In the constellation Sagittarius, 26, 0 light-years from Earth, something unspeakable lurks in the darkness. It's invisible, it's massive beyond comprehension, and it's hungry. Hey everyone, welcome to my channel. If you're new here, make sure to hit that subscribe button and turn on notifications so you don't miss any of my latest videos. I really appreciate your support, and it helps me continue creating content for you all. Now, let's dive into today's video. For centuries, we've gazed up at the Milky Way, unaware that at its very heart lies a monster so powerful it could devour our entire solar system without breaking a cosmic sweat. This is Sagittarius A star, Sgr A for short, a supermassive black hole 4 million times more massive than our Sun. This is the story of humanity's greatest cosmic detective work, how we discovered the invisible giant that holds our galaxy together, and what it means for our understanding of the universe itself. Invisible giant. Our story begins not with what we can see, but with what we can't. Black holes, by definition, don't emit light. They're cosmic vacuum cleaners so powerful that not even light can escape their gravitational pull. So how do you find something that's designed to hide? In 1931, a Bell Labs engineer named Karl Jansky was trying to track down radio interference that was plaguing transatlantic phone calls. What he found instead changed astronomy forever. Jansky discovered that radio waves were coming from the center of our galaxy, mysterious signals from the direction of Sagittarius. But Jansky couldn't have known he was detecting the first whispers of a monster. By the 1960s, radio astronomers had pinpointed an intense radio source at the galactic center. They called it Sagittarius A, the brightest radio source in the constellation. But this wasn't just any cosmic radio station. The signals were coming from something incredibly compact and incredibly energetic. Imagine trying to pinpoint a whisper in a hurricane. The galactic center is a cosmic maelstrom, dense clouds of gas and dust, ancient stars, and violent stellar explosions. But buried within this chaos, something was generating radio waves with surgical precision. The early radio observations were like hearing a symphony through static. We knew something extraordinary was conducting the orchestra at the galactic center, but we couldn't see the conductor. By the 1970s, astronomers had subdivided Sagittarius A West, a swirling disk of hot gas. And at the very center, something they called Sagittarius A star, Sgr A. This tiny radio source, no bigger than Mercury's orbit around the Sun, was about to rewrite our understanding of gravity, space, and time itself. The stellar dance. To catch a monster, you need the right tools. By the 1990s, astronomers had developed infrared telescopes capable of peering through the dust and gas that shrouds our galactic center. What they found was extraordinary. Stars, hundreds of them, crowded into a space smaller than our solar system. But these weren't ordinary stars, they were moving at impossible speeds, whipping around the galactic center like cosmic race cars. When we first saw these stellar orbits, we couldn't believe our eyes. Stars traveling at 50 kilometers per second, that's over 11 million miles per hour. Something with incredible gravitational pull had to be controlling their motion. Two teams of astronomers, one led by Reinhard Genzel in Germany, another by Andrea Ghez at UCLA, embarked on one of the most ambitious observation campaigns in astronomical history. For over 2 decades, they tracked individual stars as they danced around the galactic center. One star, dubbed Stu, became their smoking gun. Every 16 years, Stu completes a dramatic elliptical orbit around Sgr A. At its closest approach, it screams past at 650 kilometers per second, nearly 3% the speed of light. But here's the remarkable thing. There's nothing visible at the center of Stu's orbit. The star is racing around, empty space. Using Newton's laws of orbital mechanics, the same principles that govern planets around our sun, astronomers calculated the mass of whatever was tugging on STU. The result was staggering. 4 million times the mass of our sun, compressed into a region no larger than Mercury's orbit. Imagine trying to squeeze 4 million suns into the space of Mercury's orbit around our sun. There's only one known object in the universe dense enough to achieve that: a black hole. By 2002, the evidence was overwhelming. Sgr A wasn't just a mysterious radio source, it was a supermassive black hole, the gravitational anchor point of our entire galaxy. But discovering the monster was just the beginning. The real question was, what was it doing to our galaxy? Anatomy of a monster. To understand Sagittarius A, we need to understand what makes a black hole tick. Einstein's theory of general relativity describes them as regions where space-time itself becomes so warped that nothing, not even light, can escape. Picture a bowling ball placed on a stretched rubber sheet. The ball creates a depression, and if you roll marbles nearby, they'll spiral toward the ball. Now imagine the ball is so heavy it punches a hole clean through the sheet. That's essentially what a black hole does to the fabric of space and time. Black holes are the ultimate expression of Einstein's theory. They're places where the normal rules of physics break down, where time slows to a crawl, and where the very concept of inside and outside becomes meaningless. Sgr A has 3 key features that define its monstrous nature. First, its event horizon, the point of no return. For our galactic monster, this invisible boundary has a diameter of about 24 million kilometers. That's roughly 40 times the distance from Earth to the Moon. Cross that line, and you're committed to a one-way journey to, well, nobody knows. The math suggests a singularity, a point of infinite density where the laws of physics collapse. But that's a mystery for another day. Second, there's the accretion disk, a swirling maelstrom of superheated matter spiraling into the black hole. As gas and dust accelerate towards Sgr A, friction heats the material to temperatures exceeding 100 million degrees. At these temperatures, matter doesn't just glow, it screams in X-rays. But here's what makes Sgr A unusual among supermassive black holes. It's surprisingly quiet. Most black holes of this size are voracious feeders, constantly devouring nearby matter and blazing like cosmic lighthouses. Our galactic monster, by comparison, is on a diet. If Sgr A were actively feeding, the radiation would sterilize life on Earth. We're lucky to live around such a well-behaved monster. It's like having a sleeping dragon in your basement. The third defining feature is perhaps the most mind-bending. Sgr A is spinning. Our monster rotates, dragging space-time along with it like honey on a spoon. This effect, called frame dragging, means that near the black hole, the very fabric of reality is being stirred. These 3 characteristics, the event horizon, the accretion flow, and the spin, make Sgr A natural laboratory for testing Einstein's most extreme predictions. And in 2019, we finally got our first close-up look at the monster. First, light from darkness. April 10, 2019. News conferences around the world. Scientists barely containing their excitement. After decades of indirect observation, humanity was about to see the unseeable, the first image of a black hole. The Event Horizon Telescope, a planet-sized array of radio dishes working in perfect synchronization, had achieved the impossible. They had photographed the shadow of a black hole. But this wasn't Sgr A. This first image showed Milky Way, a supermassive black hole 55 million light-years away. Sgr A would have to wait its turn. Imaging Sgr A was actually much more challenging than Milky Way. Even though it's closer, it's also much smaller and more active. It's like trying to photograph a small, hyperactive child instead of a large, patient adult. The challenge was immense. Sgr A changes its appearance on timescales of minutes, not days. The swirling hot gas around the black hole moves at significant fractions of the speed of light, creating a constantly shifting dance of light and shadow. The Event Horizon Telescope had to capture multiple images simultaneously, then use sophisticated algorithms to reconstruct the monster's appearance. It was like assembling a jigsaw puzzle, where the pieces kept changing shape. May 12, 2022. 3 years after the first black hole image, the wait was over. There it was, Sagittarius A, the monster at the center of our galaxy. Not black, as the name suggests, but glowing with an orange-red ring of superheated matter. At the center, a shadow, darker than the deepest night. This wasn't just a photograph. It was validation of Einstein's century-old theory, proof of decades of painstaking observation, and humanity's first direct glimpse of the gravitational anchor that keeps our galaxy from flying apart. When I saw that image, I felt like I was looking at the beating heart of our galaxy. This is the object that, in many ways, made our existence possible. Without Sgr A, there would be no Milky Way, no solar system, no us. The image revealed that Sgr A looked remarkably similar to MADI 7, a validation of Einstein's theory that black holes, regardless of their size or location, behave according to the same fundamental principles. But the image raised as many questions as it answered. What was this monster doing during the billions of years before we arrived on the scene? And what role did it play in shaping our galaxy? Birth of a monster. To understand Sgr A, we need to travel back in time, way back, 13.8 billion years ago. The universe was born in the Big Bang. For the first few 100 million years, it was a dark place, filled with hydrogen and helium, but no stars, no galaxies, and no monsters. Then something extraordinary happened. Gravity began sculpting the cosmos, pulling matter together into the first stars. These ancient giants burned bright and died young, exploding as supernovae and leaving behind stellar mass black holes, typically just a few times heavier than our sun. But how do you get from a black hole weighing a few solar masses to a monster weighing 4 million? This is one of modern astronomy's greatest puzzles. Creating a supermassive black hole is like trying to grow an oak tree overnight. The standard process of stellar collapse and gradual feeding simply doesn't work fast enough. We need alternative theories. Theory number 1, the direct collapse model. In the early universe, massive clouds of primordial gas might have collapsed directly into intermediate mass black holes, weighing thousands of solar masses. These seed black holes could then feed voraciously on surrounding matter. Theory number 2, stellar mergers. In the dense stellar environments of the early universe, massive stars might have collided and merged repeatedly, creating ever larger black holes through cosmic cannibalism. Theory number 3, primordial black holes. Some cosmologists speculate that black holes of various sizes might have formed directly in the Big Bang itself, seeded by quantum fluctuations in the early universe. The truth is, we're still solving this mystery. Recent observations from the James Webb Space Telescope are showing us supermassive black holes that existed when the universe was less than 1 billion years old. These monsters grew incredibly fast, faster than we thought possible. What we do know is that Sgr A has been with our galaxy almost from the beginning. As the Milky Way formed from merging smaller galaxies, our monster was there, growing alongside the stellar disk that would eventually become our cosmic home. But the relationship between Sgr A and our galaxy isn't one-sided. The monster doesn't just live in the Milky Way, it actively shapes it. The Puppet Master. For decades, astronomers assumed that supermassive black holes were just passengers in their galaxies, massive objects that happened to sit at galactic centers without much influence on their surroundings. They couldn't have been more wrong. Modern research has revealed that supermassive black holes like Sgr A are cosmic puppet masters, controlling the evolution and structure of their entire galaxies through a process called feedback. When a supermassive black hole feeds, it doesn't just swallow matter quietly. It launches powerful jets and winds that can heat gas throughout the galaxy, regulating star formation over millions of light years. Here's how it works. When material falls towards Sgr A, it doesn't all cross the event horizon. Some of it gets accelerated to near light speeds and launched back into space as relativistic jets, cosmic blowtorches that can extend for thousands of light years. These jets, along with intense radiation and stellar winds, create what astronomers call a feedback loop. The black hole feeds on gas, then uses that energy to heat and disperse more gas, temporarily starving itself. It's a cosmic thermostat that regulates galaxy growth. But Sgr A's influence goes even deeper. Computer simulations suggest that without supermassive black holes, galaxies would be very different places, perhaps too active and chaotic for stable planetary systems to form. There's a remarkable correlation between the mass of a galaxy's central black hole and properties of the galaxy itself. It's as if the black hole and galaxy grow up together, each influencing the other's development. This relationship extends to the formation of elements essential for life. The jets and winds from feeding black holes distribute heavy elements forged in stellar cores throughout their galaxies, enriching the cosmic soup from which future stars and planets will form. In a very real sense, we owe our existence to monsters like Sgr A. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all were processed through generations of star formation regulated by our galaxy's central black hole. But what does the future hold for our galactic monster? Sgr A isn't done with us yet. The idea that a black hole might lurk at the center of our galaxy was tantalizing but difficult to prove. Black holes, by definition, don't emit light. They can only be detected indirectly through their gravitational effects on nearby matter. To prove that Sgr A was a black hole, astronomers would need to demonstrate that something incredibly massive was occupying an impossibly small volume of space. This challenge would require a new generation of telescopes and a new approach to astronomy. It would require looking at the galactic center not in visible light, which is absorbed by intervening dust clouds, but in infrared radiation, which can penetrate the cosmic fog that shrouds our galaxy's heart. The breakthrough came in the 1990s with the development of adaptive optics sophisticated systems that could compensate for the blurring effects of Earth's atmosphere in real time. These systems used deformable mirrors that changed shape hundreds of times per second, guided by computer systems that analyzed atmospheric distortions and corrected for them. With adaptive optics, infrared telescopes could finally achieve the resolution needed to study individual stars near the galactic center. And what they found was extraordinary. The galactic center wasn't empty. It was crowded with stars, hundreds of them packed into a region smaller than our solar system. These weren't ordinary stars either. They were massive, luminous giants that burned with the intensity of thousands of suns, and they were moving at impossible speeds. Imagine standing on a cosmic highway and watching cars race by at 11 million miles per hour. That's essentially what astronomers were seeing at the galactic center. Stars, objects with masses comparable to our sun, were whipping around the galactic center at velocities that should have torn them apart. Two teams of astronomers embarked on one of the most ambitious observational campaigns in astronomical history. Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany assembled a team using the Very Large Telescope in Chile. Andrea Ghez at UCLA led a competing team using the Keck Observatory in Hawaii. Both groups had the same goal: track individual stars over many years to map their orbits around whatever was lurking at Sgr A. This was astronomical detective work at its finest. Each team had to develop new techniques for identifying and tracking stars in the crowded, chaotic environment of the galactic center. They had to account for the motion of Earth around the sun's motion through the galaxy, and the effects of atmospheric turbulence. They had to calibrate their instruments with extraordinary precision and develop new methods for analyzing their data. The work required incredible patience. Stars near the galactic center move quickly by astronomical standards, but quickly in astronomy still means years to complete a single orbit. The teams had to observe the same stars night after night, year after year, slowly mapping their celestial dance. One star became their smoking gun, STU, also known as Sgr A. This massive blue giant follows a highly elliptical orbit that brings it closer to Sgr A than any other star they could track clearly. Every 16.05 years, STU completes its orbital journey, diving to within 120 astronomical units of the galactic center, closer than Pluto is to our Sun. At its closest approach to Sgr A, STU reaches a velocity of 650 kilometers per second. That's 2.55% the speed of light. To put this in perspective, if STU were a car traveling at this speed, it could circle Earth's equator in less than 3 seconds. But here's the remarkable thing. There's nothing visible at the focus of STU's orbit. The star is racing around empty space, or what appears to be empty space. Using Newton's laws of orbital mechanics, the same principles that govern planets around our Sun, astronomers could calculate the mass of whatever was controlling STU's motion. They could treat STU like a cosmic scale, weighing the invisible object at the galactic center by measuring how it affected the star's orbit. The calculation was straightforward in principle, but required extraordinary precision in practice. The teams had to measure STU's position to accuracies of milliarc seconds, equivalent to resolving a dime on the surface of the Moon as viewed from Earth. They had to account for relativistic effects predicted by Einstein's theory of general relativity. They had to consider the gravitational influences of other nearby stars and gas clouds. When they crunched the numbers, the result was staggering. The invisible object controlling STU's orbit had a mass of approximately 4 million times that of our Sun. This mass was concentrated within a region no larger than about 200 astronomical units smaller than the orbit of Pluto. To appreciate just how dense this object is, consider this thought experiment. If you could somehow gather together 4 million stars like our Sun and compress them into the space occupied by Pluto's orbit, the resulting density would be incomprehensible by everyday standards. The only known type of object in the universe capable of achieving such extreme density is a black hole. But the evidence didn't stop with STU. The astronomy teams tracked dozens of other stars, each following its own elliptical orbit around the galactic center. Stars like S38, which zips around Sgr A in just 19 years. Stars like S55, whose orbit is tilted at an extreme angle relative to the galactic plane. Each star provided another data point, another confirmation that something with the mass of 4 million suns was lurking invisibly at the center of our galaxy. By 2008, the evidence was overwhelming. Both the Genzel and Ghez teams published papers concluding that Sgr A was beyond reasonable doubt a supermassive black hole. The discovery earned both researchers the 2020 Nobel Prize in Physics, recognition for work that fundamentally changed our understanding of the cosmos. But discovering the monster was just the beginning. The real question was, what was this cosmic leviathan doing to our galaxy? To understand Sagittarius A, we need to understand what makes a black hole tick. The concept of a black hole emerged from Einstein's theory of general relativity, published in 1915. Einstein showed that massive objects warp the fabric of space-time itself, creating the effect we perceive as gravity. Imagine a bowling ball placed on a stretched rubber sheet. The ball creates a depression in the sheet, and if you roll marbles nearby, they'll curve toward the ball, following the warped geometry of the surface. This is analogous to how mass warps spacetime, causing objects to follow curved paths we interpret as gravitational attraction. Now imagine the bowling ball becomes so massive and dense that it punches a hole clean through the rubber sheet. That's essentially what a black hole does to spacetime. It creates a region where the curvature becomes so extreme that space and time lose their normal meaning. The boundary around this region is called the event horizon, the point of no return beyond which nothing, not even light, can escape. For Sgr A, this invisible boundary has a diameter of about 24 million kilometers. That's roughly 40 times the distance from Earth to the Moon, or about 1/6 the distance from Earth to the Sun. Cross the event horizon, and you're committed to a one-way journey toward the black hole's center, where Einstein's equations predict a singularity, a point of infinite density and zero volume, where the laws of physics as we know them break down completely. What actually happens at a singularity remains one of the deepest mysteries in physics. But black holes aren't just cosmic drains that swallow everything around them. They're dynamic, complex objects that can interact with their environment in remarkable ways. When matter falls toward a black hole, it doesn't simply disappear. It puts on one of the most spectacular light shows in the universe. As gas and dust spiral towards Sgr A, they form what astronomers call an accretion disk, a swirling maelstrom of superheated matter. Friction between particles in this disk generates tremendous heat, raising temperatures to hundreds of millions of degrees. At these extreme temperatures, matter doesn't just glow, it blazes with X-ray and gamma-ray radiation. The accretion process is incredibly efficient at converting matter into energy. Einstein's famous equation, E·mc², tells us that mass and energy are equivalent, and black holes are the most efficient engines for mass-to-energy conversion in the universe. A black hole can convert up to 42% of an object's rest mass into energy as it falls past the event horizon, far more efficient than nuclear fusion, which converts less than 1% of mass to energy. But here's what makes Sgr A unusual among supermassive black holes. It's remarkably well behaved. Most black holes of comparable mass are voracious feeders, constantly devouring nearby matter and shining like cosmic lighthouses. Astronomers call these active galactic nuclei, or AGN, and they can outshine entire galaxies with their brilliance. Our galactic monster, by comparison, is on a strict diet. Sgr A consumes only about 1 Earth mass worth of material per year, a tiny fraction of what's available in its vicinity. If it were feeding at maximum capacity, the radiation it produced would sterilize life throughout much of our galaxy. We're fortunate to live around such a considerate monster. This raises fascinating questions about Sgr A's feeding behavior. Why is it so inactive compared to other supermassive black holes? Part of the answer lies in the nature of the material surrounding it. The gas near Sgr A is extremely hot, tens of millions of degrees, which makes it difficult for the black hole to capture efficiently. Hot gas moves fast, and much of it flows past the black hole rather than falling in. Additionally, Sgr A appears to be in a low accretion state where magnetic fields play a crucial role in controlling the flow of matter. These fields can act like cosmic traffic police, directing some material toward the black hole while deflecting other material away. The third defining characteristic of Sgr A is perhaps the most mind-bending. It's spinning. Our monster rotates at a significant fraction of the maximum possible rate for a black hole of its mass. This rotation drags space-time along with it, like honey stirred by a spoon. The effect, called frame dragging, or the Lense-Thirring effect, means that near Sgr A, the very fabric of reality is being twisted and stirred. This rotation has profound implications for how matter behaves near the black hole. It affects the structure of the accretion disk, influences the launching of relativistic jets, and determines the precise location of the innermost stable circular orbit, the closest distance at which matter can orbit the black hole without inevitably falling in. These three characteristics, the event horizon, the accretion process, and the spin, make Sgr A a natural laboratory for testing Einstein's most extreme predictions. And in the 21st century, we finally developed the technology to observe these effects directly. The quest to image a black hole represents one of the most ambitious technical achievements in the history of astronomy. The challenge is almost impossible to comprehend. How do you photograph something that, by definition, emits no light? The answer lies in observing not the black hole itself, but its shadow, the dark silhouette it creates against the glowing matter surrounding it. Even this approach requires telescopic resolution far beyond anything achievable with conventional instruments. To understand the technical challenge, consider that Sgr A has an angular size, as seen from Earth, of about 50 microarc-seconds. That's equivalent to viewing a DVD on the surface of the Moon. No single telescope on Earth or even in space has the resolution to discern such tiny details. The solution was to create a virtual telescope the size of our entire planet. The Event Horizon Telescope, or EHT, is a network of radio observatories around the world that work together using a technique called very long baseline interferometry. By precisely synchronizing observations made simultaneously at different locations, astronomers can achieve the resolution of a telescope as large as the separation between observing sites. The EHT network includes radio telescopes in locations as diverse as Hawaii, Arizona, Spain, Chile, Mexico, and even the South Pole. Each telescope observes the same cosmic target at exactly the same time, recording not just the intensity of radio waves, but also their precise phase information. Later, supercomputers combine these observations, effectively creating an Earth-sized radio telescope. But the technical challenges of the EHT go far beyond simply linking telescopes together. The project required advances in atomic clock technology to synchronize observations with nanosecond precision. It required new data recording systems capable of capturing information at rates of multiple gigabytes per second. It required sophisticated algorithms to reconstruct images from incomplete and noisy data. Perhaps most challenging of all, it required understanding the target itself. Unlike photographing a static object, imaging a black hole means capturing something that changes on timescales of minutes. The hot gas around Sgr A moves at significant fractions of the speed of light, creating a constantly shifting pattern of light and shadow. The EHT team's first target wasn't Sgr A, but rather MADI 7, a much larger supermassive black hole in the center of the galaxy. MADI 7, located 55 million light-years away. Although MADI 7 is much more distant than Sgr A, it's also much larger and more stable, making it an easier target for first-generation imaging attempts. On April 10, 2019, the world got its first look at a black hole. The image of MADI 7 showed exactly what Einstein's theory predicted: a bright ring of glowing matter surrounding a dark central shadow. The shadow wasn't perfectly circular. General relativity predicts that the spinning black hole should create an asymmetric brightness pattern, with one side appearing brighter due to relativistic beaming effects. The observations matched the theory with stunning precision. But Sgr A remained elusive. The smaller, more variable nature of our galactic center black hole made it a much more challenging target. The EHT team had to develop new imaging techniques that could account for the rapid changes in Sgr A's appearance. They had to create multiple images simultaneously, and then use sophisticated algorithms to average out the variations. The breakthrough came after 3 years of intensive data analysis. On May 12, 2022, the EHT team revealed the first image of Sagittarius A, the monster at the center of our own galaxy. The image was both familiar and remarkable. Like MADI 7, Sgr A appeared as a bright orange ring surrounding a dark central shadow. The ring showed the same asymmetric brightness pattern predicted by general relativity. The shadow's size matched theoretical predictions for a black hole of Sgr A's mass and distance. But this wasn't just a photograph. It was validation of a century of theoretical physics and decades of observational astronomy. The image proved that Einstein's century-old theory of general relativity accurately describes the behavior of matter and spacetime under the most extreme conditions in the universe. The image also revealed subtle differences between Sgr A and Milky Way. The ring around our galactic center black hole appeared more turbulent, with brighter and dimmer regions that shifted on timescales of minutes. This variability reflects the more chaotic environment around Sgr A, where hot gas swirls and eddies in the black hole's immense gravitational field. Analysis of the image provided new insights into the physics of black hole accretion. The brightness asymmetries revealed information about the rotation of Sgr A and the structure of magnetic fields in its vicinity. The size of the shadow confirmed the black hole's mass with unprecedented precision. Perhaps most remarkably, the image showed that black holes, regardless of their size or location, behave according to the same fundamental principles. The similarity between Sgr A and Milky Way, despite their vastly different masses and environments, demonstrated the universal nature of Einstein's theory. But the significance of finally seeing Sgr A extends far beyond confirming theoretical predictions. This image represents humanity's first direct glimpse of the gravitational anchor that keeps our galaxy from flying apart, the cosmic engine that has shaped the evolution of the Milky Way for billions of years. To understand Sgr A's role in our cosmic history, we need to travel back in time, way back, to the very beginning of the universe itself. 13.8 billion years ago, the universe began in the Big Bang, emerging from a state of incredible density and temperature that we still don't fully understand. In those first moments, space itself expanded faster than light, inflating from quantum scales to macroscopic dimensions in a tiny fraction of a second. For the first few 100,000 years, the universe was opaque, a hot, dense soup of protons, electrons, and photons that scattered off each other continuously. Light couldn't travel far before being absorbed or scattered, making the cosmos a dark, formless place. But as the universe expanded, it cooled. Eventually, temperatures dropped enough for protons and electrons to combine into neutral hydrogen atoms. This moment, known as recombination, occurred about 380 years after the Big Bang. Suddenly,